Meet Duncan. Duncan is a typical 8-year-old. He is friendly, likes playing baseball and video games, and loves pizza. In the past year, Duncan's parents have noticed he is more active than his peers. After his activities are over, he has trouble sitting still to talk to his friends. At home, his room is a mess, and he seems to not listen when his mother speaks to him directly. Duncan is very smart, but he is having new trouble in school. During a parent-teacher conference, his parents are surprised to learn he interrupts other kids, seems unable to sit still in his chair, and fidgets throughout the day. He also seems to not follow directions and makes careless mistakes on many of his math problems. What is happening to Duncan? While it is tempting to say this is just a phase and Duncan will grow out of it, it is important to note that his set of behaviors is different from other kids his age and is leading to significant impairment at school and at home. A discerning clinician will recognize that Duncan is exhibiting symptoms of attention deficit hyperactivity disorder, or ADHD. ADHD is a brain disorder characterized by a pattern of inattention with or without hyperactivity and impulsivity that leads to impairment in functioning. The major functions a child needs to complete are going to school, learning to behave in a family, and making friends. Mastering these functions is vital to social, cognitive, and emotional development. Learning about what happens in the brain of someone with ADHD highlights the ways ADHD can disrupt development in these areas. What is different about Duncan's brain from other kids his age? There are many different changes in brain processes involved in those with ADHD, but not everyone with ADHD has each of these changes. What does that mean? Two kids with ADHD can look very different. Children with ADHD can have differences in the structure or function of brain pathways that control multiple cognitive functions. Here, we will focus on attention, anticipation of and response to reward, executive functioning, and motor control. Let's take a quick look at each one. One of the most important aspects of cognitive functioning is the ability to sustain attention on a single task and to shift attention between different tasks when necessary. The frontoparietal network is involved in the directing of attention during goal-oriented tasks. This network consists of several interconnected structures, including the dorsolateral prefrontal cortex, dorsal anterior cingulate, lateral frontal pole, inferior parietal cortex, and the lateral cerebellum. This system is particularly important in visuospatial attention. In ADHD, there is less activation of this network during tasks that require directed focus or the shifting of attention. What does this look like clinically? Imagine a child doing a chemistry experiment involving the observation of multiple moving parts. If they cannot focus on their measurements and shift their attention appropriately to complete the experiment, things might not go quite as planned. When something unexpected happens, the brain has to decide quickly whether the new stimulus is worthy of its attention. This is a very important cognitive task that is frequently affected in ADHD. The ventral attention network is responsible in shifting attention to unexpected but relevant stimuli. This network consists of the temporoparietal junction, anterior insula, and the inferior frontal gyrus. In ADHD, there is less activation in the connections of this network when an important and surprising cue is presented. What does this look like clinically? Imagine a child who is super engaged in a game on their phone. When his or her mother walks into the room and announces it is time for dinner, a child with ADHD may be less likely to notice or respond to this important cue. You can imagine how this might go over with the mother in this scenario. It can often appear a child with ADHD is not listening when they are addressed. Despite having billions of neurons, the brain is constantly fighting over cognitive resources. The default mode network is involved in attending to internal cues and is competing for attentional resources with systems involved in external focus. This network involves several interconnected structures, including the medial prefrontal cortex, posterior cingulate cortex, medial temporal lobe, and lateral parietal cortex. The default mode network is typically active when someone is at rest and preoccupied with internal cues, and inactive when someone is attending to external cues. Therefore, this network is usually in anti-correlation with other attentional networks, kind of like a seesaw. In ADHD, there is more activation of the default mode network and less resting anti-correlation with attentional systems involved in external focus. What does this look like clinically? A classic example is a child with ADHD daydreaming in class while the teacher is giving a lesson. This child would have difficulty dividing their attentional resources between internal and external cues, and might appear to be in their own world. The ability to delay gratification is an essential developmental task implicated in social and emotional well-being. Without it, children may give in to what is more immediately exciting instead of waiting for what they really want. This task of delaying gratification, conceptualized here as reward anticipation and processing, is commonly affected in children with ADHD. The reward circuit consists of several structures, such as the ventromedial prefrontal cortex, amygdala, ventral tegmental area, and the striatum, particularly the ventral striatum, which includes the nucleus accumbens. In children with ADHD, there is less activation of the ventral striatum during the anticipation of rewards. Therefore, to seek more activation, children with ADHD may act to receive immediate gratification rather than a later reward that they might be more interested in. What does this look like clinically? Children with ADHD may have more difficulty with real-life marshmallow tests than their peers. Imagine a mother who promises a child a new, expensive Lego set for completing their homework one afternoon. Despite being very interested in this Lego set, a child with ADHD may instead play a game on their phone that is somewhat interesting to them at the time and definitely more immediately rewarding to them than doing their homework and earning the larger reward. Some of the most important skills we learn as we get older are to be able to plan and organize. These executive functions allow us to navigate social interactions, succeed in jobs and school, and plan for our future. Executive functioning is a cognitive domain commonly affected in children with ADHD. Two executive functioning networks involved in ADHD are the corticocerebellar and executive control networks, which work together to help children complete more complex tasks. These systems have several overlapping structures. In the corticocerebellar network, signals from the prefrontal cortex travel through subcortical structures in the basal ganglia to the cerebellum, returning signals and feedback through the thalamus. In executive control networks, signals from the prefrontal cortex travel through the dorsal anterior cingulate and basal ganglia, with feedback returning through the thalamus. In children with ADHD, there is less functional connectivity and lower levels of activation in these networks. What does this look like clinically? Kids with ADHD may have many difficulties in their executive functioning, such as completing multi-step problems in school, organizing their room, and making schedules and plans. Someone like Duncan, who is very smart, may go unnoticed in terms of learning difficulties until the schoolwork becomes harder and more demanding. Movement is essential in helping children learn about and navigate their external environment. However, difficulty constraining or planning movement can lead to significant impairment as a child gets older. Hyperactivity in children with ADHD is one of the most noticeable symptoms to others, and may get kids into trouble with their teachers and peers. There are surprisingly few studies looking into the underlying cause of hyperactivity in ADHD, but there is some suggestion that motor symptoms can involve higher levels of baseline motor activity, difficulties with motor planning, and decreased ability to suppress motor impulses. This may be due to decreased activity in the caudate and putamen, supplementary motor area, premotor cortex, medial superior frontal gyrus, and right medial prefrontal cortex. There may also be structural differences, such as lower basal ganglia volume. What does this look like clinically? Kids with ADHD can look and feel like they are driven by a motor. A hyperactive child in school may squirm in their seat, stand up and walk around inappropriately, and climb onto furniture. Poor motor planning can also make a child with ADHD seem pretty clumsy. The good news is that ADHD is very treatable. Now that we have an understanding of the brain pathways that underlie ADHD symptoms, we can see how the recommended treatments for ADHD actually work. Treatment of ADHD can involve medications and behavioral strategies. The pathways we reviewed, especially those falling within frontostriatal areas, are rich in dopaminergic and noradrenergic neurons and are less active in ADHD. Medications for ADHD tend to increase dopamine and norepinephrine levels in these areas. Medications fall into two categories: stimulant and non-stimulant. Stimulants include amphetamines, which act to release more catecholamines into the synapse, or methylphenidate, which reduces the reuptake by blocking the transporter, leaving higher levels in the synapse. Non-stimulant medications include atomoxetine, which inhibits the reuptake of norepinephrine, and alpha-2A agonists, such as guanfacine, that mimic endogenous norepinephrine by stimulating postsynaptic alpha-2A receptors and are thought to improve functional connectivity in the prefrontal cortex. Behavioral strategies in ADHD correspond to the symptom domains we discussed. For example, seating a child in the front of the classroom may reduce extraneous stimuli and improve attention. Creating a behavior chart where a child earns stickers as soon as they engage in desirable behavior can capitalize on a child's desire for immediate rewards and can shape behaviors through positive reinforcement. A parent may help plan the child's homework schedule and create to-do lists with them, helping a child with their executive functioning. Scheduling intermittent breaks during the school day, or signing a child up for a sports team, may help with symptoms of hyperactivity. ADHD is a treatable condition that may involve underlying brain pathways involved in attention, reward anticipation, executive functioning, and motor control. Of course, kids with ADHD can have different involvement of these brain pathways, leading to very different clinical presentations and individualized treatment strategies. For example, Duncan is hyperactive, interrupts other kids, does not listen, and works through his math problems carelessly. Duncan may benefit from medication, scheduled breaks during the school day, organized sports, and individual attention while completing assignments. We can also imagine another child with ADHD, who is quiet in class but is falling behind because she cannot organize herself to complete increasingly long and difficult assignments. She may also benefit from medication, as well as preferential seating, creating checklists, and extra time on tests. A third child with ADHD may get easily frustrated, hit his classmates, throw tantrums at home, and have difficulty getting started with homework. This child may also benefit from medication, as well as a sticker chart that rewards safe and desirable behaviors. For each of these very different children, proper treatment of their ADHD can put them on the track for emotional, social, and academic success.